Okay, so this is today's lecture summary. Can you bring up the mask? Yeah, I begin to, there are some signature sheet here. It's really, let me call this really team lecture summary sheets, okay? Rather than signature sheet, so probably I would change the name so to emphasize that this is teamwork to summarize rather than an individual student would write everything, and so to finish everything quickly. Okay, so please keep this in mind. The lecture summary procedure is that there should be a teamwork, that each team member would contribute at least a point to the summary before you sign, right? That would be the ideal case. And instead of a single student would write everything, and then one can get done quickly. Right? And the next, the quotation in the box is what I just mentioned. I mentioned last lecture. That's a quotation by Montesquieu. And it reads, intelligence consists of this, that we recognize the similarity between different things and the difference between similar things. Okay, you can read about Montesquieu, and there's a page in the book where this quotation is was mentioned. I'd like to move forward to provide you with yet more big picture. There's nothing but big picture. Okay, so if one does not see the big picture, there may be a problem of understanding rather than there's a lack of big pictures. You have seen the Taylor series expansion, right? And I have mentioned to you the usefulness of that to be able to solve scalar second order differential equations excited by advanced functions like log of 1 plus t. But let me pose this critical thinking question. How do you solve the matrix equation of motion for the model problem in the first half of the semester as excited by, say, for example, log of 1 plus t? Anyone? Let me give you a hint. And the hint is in the section 53, let me leave 53C and 53E. Okay. And while you're thinking about that, let me bring up 53C and 53E. Okay. And in 53C, on the left here, I showed you or remind to you the system that we use to start the semester. And on 53E, right, a few sections later, I give you a hint. And all you need is to come up with a plausible answer, right, to my question. How do you excite? Okay, how do you excite this system here? Meaning the force F1 or F2 can have log of 1 plus t. Okay, can contain the function, the advanced function like log of 1 plus t. Something that is really, really advanced. And the hint is right here on the right. In this section 53E, which all of you have seen. So to answer this question, you can use what I projected as a hint and just put together a coherent story, right? Anyone? One more hint. Look at this function h of t here. Remember, and divide it into two cases. You know, h of t is a function of t that you can dream of any function, right? Sine, cosine, constant. How about log of 1 plus t? That was case 2. Case 1 was h of t equal to 1, a constant. So now if you stick h of t as log of 1 plus t, that becomes really advanced, right? That's challenging. That's more than what the vibration course would teach you. This can be called advanced vibration, if you like. So you would already have advanced vibration before you actually take the vibration course. Okay. But then how do you solve this system as excited by something that has log of 1 plus t in it? Can someone provide a coherent story? This is what I call critical thinking, right? Instead of memorizing. Anyone? How do you know, if you are exciting this system here, driven this system, if you drive this system by an applied force that has the function log of 1 plus t, how would you solve the problem? Colton, anyone else?
You convert the excitation, the h of t, into a Taylor series expansion, and then you just solve the rest of the problem like we did before.
Okay, so Colton said convert log of 1 plus t into Taylor series and solve it. But you know, remember that this is a system of coupled differential equation. Okay, I mean, what you said is in the right direction, but I'd like you to fill in the gap as a review for the class. What do you need to do, you know, before the van?
Is it kind of like when you need to originally break the uncoupled distribution into our two modules?
Yeah, decouple the system into two uncoupled, right, linear second order differential equation. So once you have the uncoupled differential equation, then you can solve each one easily. And then you follow what Colton was saying, expand log of 1 plus t into Taylor series, and then you have power series to solve, right, for each of the modal equation. Let's write down here. Okay, so these are the two uncoupled systems. Let me zoom in. And it even has still bear the mark of a general treatment, h of t. So now h of t would figure in here, log of 1 plus t, example. And you can expand log of 1 plus t into Taylor series. Then you can solve for mode 1 or the modal displacement y1, right? And then solve for the modal displacement y2 and then combine together. Okay, so that's the big picture of that. So this, for this type of problem, the vibration course would not even address. Okay, so that's the big picture. And I move on to, like I said, you know, I want to really coach the class to solve the all 4 problems, in addition to having the solution guides that you already have. And so last time I already went through the basics of projections for vectors and have introduced the gram matrix. Okay. And today I'd like to really, I'm anxious to get into the street fighting function projection as a direct generalization of what you saw with vectors. Okay, and let me bring up section 8, B. Okay, so vectors, this is the example. Okay, this is basically, if you want, this is the theory. The examples, as I mentioned, is given in the form of a problem here, where this one here, where you have the vector v is given, and the vector, the basis vectors are also given. Okay, so let me bring up a bigger window. So to zoom in. All right, and let me just help you, because once you see the formulation with numbers, most students would have a better feel. Okay, so I'd like to help with this. Oh, by the way, there are the team lecture summary sheets and some handwritten notes that I have from last time. You know, if anyone would like to have a copy, so please help us out. Okay. So here you see the vector v is given in Cartesian coordinates, given because you know the components, right? And the oblique vectors b1 and b2 are also given because you know the components of b1 and b2 in the Cartesian coordinate system, right? So the question is to find the component c1 and c2 here of the same vector v, but relative to the oblique coordinate system b1 and b2, right? And so the answer is already provided here. You know, in other words, the formula that you want to use is already right here. Okay, we have already derived this, so I'm not going to go back on this. The video of the lecture is available to anyone to look at. So, active learning credit. How do you set up the gram matrix and how do you compute the gram matrix? Let's do it quickly because this is just dot products, okay? So let me start with the first coefficient, and anyone, like I said, all students who raise their hands have active learning credits. How do you compute the first coefficient, b1 dot b1 of the gram matrix? Given that, you know, b1 is given here, okay? So what is b1 dot b1? Let me provide some help here.
2 plus 7.
Sorry?
2 plus 7.
Okay, so remember b1, the coefficients are 2 and 7. Let me give something that is a little suggestive. So Kevin mentioned 2 and 7, but remember, anyone can also contribute, okay, and get the credit. You can also write b1 as a matrix that has the coefficient 2 and 7. You can think of it like that, you know. But recall that b1 is really a vector that has the coefficient 2 relative to e1 and 7 relative to e2. Okay, and e1 and e2 are the basis vectors for the Cartesian coordinates. b1 and b2 are basis vector for the oblique coordinates. So let me draw a picture. A picture is worth 1,000 words. So let's do it like that, and do it like that. Right, and so for b1 and b2, let's say, let me just conceptually represents like that, okay? And I mean, these are the coordinate axes, and the actual vector, you can think of it like this. This is E1, and this is E2. And B1 and B2 are not necessarily of unit length, so let me just draw like that, okay? So, so think of this as B1 here, E1 here, and E2 here, okay? And so what's the vector V, okay? Let's recall. So let me bring all this down a little. And the vector V is given in Cartesian coordinates as having the components 4 and 2, right? So you can write V.
Is that other leg B2?
Sorry,
The other leg on the oblique coordinate system?
1 second. Kevin. So that's a given vector V. I'll come to you. Let me just draw. Okay, so just conceptually. Okay, so this would be V. Oops, I want to have the arrowhead. Right. And the same vector V here, and that's V. All right, Kevin, you have a question?
The second leg on the oblique system, is that B2?
Yeah, this is B2. I just, yeah, let me add that in, so there will be no questions on this part. So this is the same, and just have the index 2. Okay. Yeah, let's see. All right, so let me repeat my question again. You know the formula, right? The formula is right here. Okay. The gram matrix, like I said in my last lecture, all of the coefficients of the gram matrix and the right-hand side, you should know how to compute. The question is, how do you do that? This is a very concrete example, so that no one should not know how to do. Okay, so let's Kevin, anyone else? I need to note down Colton. While I do this, why don't you think, discuss with your teammates freely and contribute and get active learning credits. Very, very easy. Colton is team 2. This is meeting 35, and you have Kevin, is team 7. Anyone? Come on. Kevin, team 7. How do you compute the first coefficient? So we have John and Kevin, team 6, and Paul. What team number, Paul? Team 3. Okay, let's start with Paul.
Are you asking how you do the dot?
How to find B1 dot B1, right? You know, the angle bracket represents the dot product when you talk about vectors, but generalized to functions, it's called the scalar product of two functions. That's why we use the angle bracket. That sounds, seems more abstract, but it has a very powerful advantage of being able to generalize to functions. You cannot generalize a dot product to functions, right? It doesn't mean anything. Take a dot product of two functions. Okay, so do you have an answer for me?
It'd be 4 plus 49.
Okay, so Kevin and John, you can build on top of what,
It's just
you know, so you see B1 here has the coefficient of components as 2 and 7. So how do you find, you know, B1 scalar product or dot product with B1?
you add up the squares of the terms.
Okay. So let me write like this: B1, comma B1, angle bracket. It's the same as B1 dot with B1, and it's the same as B1 transpose times B1. Okay. And that's I'd like to present this way so that for those of you who did not catch up in the first half of the semester, you should see it now. Okay. Right. B1 transpose, the column becomes the row, and when you take the row matrix times the column matrix, you get the scalar number. So, John and Kevin, do you agree with this? Okay, that's it. This is how you compute the dot product, right? So like John said, 2 times 2 plus 7 times 7. Okay, that's the sum of the square of the components that you all know from many years ago. All right, so therefore, this new concept here is really not difficult now, I hope. Let's do one more thing, one more coefficient, and we should stop here because everyone should know by now. How about B1 dot B2 or B1 scalar product with B2? Paul? So let's first by I set up the problem for you. Let's write B2, right? So B2 is 3/2 and E1 and 3E2. So therefore B2 you can write like this, and then we'll see how you get B1. So B2 is 3/2 and 3, right? These are the components relative to the Cartesian coordinate system. So therefore, if you want to take B1 scalar product with B2, so now we can do directly. Go ahead, Paul.
So it's
What should I write here?
B1 dot B2.
B1 dot B2
And that's the same
or
as B1 transpose.
B2, right? B1 transpose B2, so we can go directly to this notation, and that's the same as the row matrix 2, 7 times the column matrix, which is 3/2 and 3. Okay, and everyone should know how to do this matrix.
I don't understand that at all, because if I was gonna do the dot product, say go back to B1 and B1, I'd dot E1 with E1 and then E2, and I'd get a 2. And then I'd dot E2 with E1 and E2 and get a 7, end up with a 9. I don't understand how you're ending up with a 50.
Okay, so the question that Kevin asked was that he didn't understand why. This is excellent. Okay, I'm glad you asked this. Why I wrote the dot product as the transpose of the matrix times itself. In fact, this really very fundamental, and everyone should really know this. And so this go back to over here. Okay, and I'm really glad you asked this because I'm sure many students really memorize rather than know this answer. Okay, but I would like to test whether my assumption was true, and I hope that you would show that I was wrong. Okay. So to explain or to answer Kevin's question, let's say if you do B1 dot B1, right? Then you can write, you can replace B1 by its expression as given here. Let me compact it so that I have more space. Right? You just replace this expression here. Right?
My bad, again. My bad.
I'm sorry?
I understand.
Oh, you understand now. Excellent. But let's see whether the class can complete the answer. Okay, so that's B1 dot B. That's B1 dot B1. Right? This is honest to God fundamental. Right? So what's the next step? How do you explain next? To get to the result of B1 transpose times B. So we have Devane. Anyone else? Okay, Devane.
Just multiply
Multiply out.
each one of the
Okay, let's multiply out Devane.
E1 by E1.
Okay.
And then E2 by E2.
Okay, so you have here 2 times 2, right? E1 dot with E1 plus 7 times 7 E2 dot with E2. That's not all, right? Because you have the cross term as well. So you have 2 times 7 E1 dot with E2, right? Is there anything else?
7 times 2, E2 dot E1.
Very good. So 7 times 2 E2 dot with E1.
Trying to do all this higher math, I forgot my arithmetic.
No. Your question is very good. So what next? What next?
The last two terms are 0
Why?
because they're orthogonal, E1 and E2.
Very good. That's it. But that's still not the answer. That's still not the complete answer. This is good. What else? Very good. What is your team number? Your name?
Andres, team set.
Team 6. Okay. Very good. Andres, yes.
Basis vector is where it is.
Very good. Excellent. Because the basis vectors E1 and E2 are called orthonormal. Their length is equal to 1. Okay, so therefore this is 1 and this is 1. That's it. We have shown that B1 is the square of the first component plus the square of the second component, and therefore can be written as B1 transpose times B1 as shown earlier. Alright? So that's the back to the basics there. And I hope all the students can catch up. So I think we have already, so if we go back to this system here, I believe that now you know how to find all of these coefficients, right? Including the right hand side. Do I need to show anymore? I hope that I don't need to. Right? Is it, if anyone who has questions, please ask. Otherwise, I assume that this is now well known. And so therefore, you have two equations, two unknowns that you can find, C1 and C2. Okay? Now let's see how to generalize to function, because that is really the power of this method. Okay? Now, to generalize to function, I already started last time. But you know, like I said, I don't want to. I want to show to you the street fighting methods. Okay, this is still abstract. It has lots of symbols. So let's go directly to the street fighting section 8C and take a very concrete example. Okay, and the concrete example is. I need to leave the window a little bit because so that the camera doesn't lose focus. Let's take a function, so for example, x to the power 5, okay? And project, now you can use the terminology projection. Project the function x to the power 5 on the basis of two functions, 1 and x. Okay? Remember, 1 is x to the power 0. Okay? So, meaning that, just like vectors before, what you want to write now, okay, so let me write something so that, let me go to the next page. So the function that plays the role of a vector now is x to the power 5, okay? That's like the vector v before. And you have, let me call b0 as x to the power 0, that is 1. And b1 is x to the power 1, that's x, okay? And you want to express f in terms of the basis functions b0 and b1 as c0 b0x plus c1 b1x, okay? Or meaning that f, which is in this case x to the power 5, but generally that's c0 times 1 plus c1 times x, okay? It's really, this is a projection and this is really an approximation, okay? Because functions are considered as vectors but infinite dimension. It has infinitely many dimensions. Okay, so this is the problem here. Find the components C0 and C1 such that you can approximate x to the power 5 in terms of 1 and x by projection. What does it mean, projection? So let's say, can someone remind the class what's the first step? You know, in finding the components C0 and C1 of, let's say, a given vector. What's the first step? You know, we just review vectors, right? I mean, from the last lecture and just now, what would be the first step? You cannot draw, you know, in statics like parallelogram anymore, right? These are functions. There's no parallelogram to draw. So you need to use a method that I explained. Yes. So
you have to convert it into the oblique coordinate system, the oblique basis.
You take what?
You have to convert it into the oblique basis.
Convert to the oblique basis. Okay. I keep. What is your team number and name again?
Team 3, Richard.
Team 3, Richard. Yes. Did I call you Richard?
Yeah.
Yeah. Because, you know, there was some student sitting here in my last lecture saying that he was confused, and I was trying to reach that student to see whether there was any further confusion after my lecture, but I must have reached the wrong, not the right student. Colton.
You're going to set up a gram matrix to solve the matrix
Do
equation.
the scalar product. You know, in a way, B0 and B1 are already like the oblique coordinates. Okay? Here we can no longer talk about, in a way you will see that this is indeed the equivalence of the oblique coordinates, and let me leave that question to answer soon. So essentially, this is what you want to do, you know, set up the system where you have the gram matrix, right, times the coefficient. So maybe perhaps I should rewrite okay, in my notes so that you can follow. You know, so like Colton said, right, you take first rewrite this system so that you move the known quantity to the right hand side, and what is unknown stay on the left. So that's the first step. Okay. And then take B0 and perform a scalar product throughout, you know, on both sides. So what you do is the following, and B0 is 1, okay? So instead of doing the general case, let me do this very concrete case here. So you take C0 and then 1 scalar product with 1 plus C1, 1 scalar product with X equal to 1 scalar product with F. Okay, that's it. 1 is B0. And then to get the second equation, what do you need to do to get the second equation? Remember, there are 2 unknowns, right? You need 2 equations. Someone? Yeah, you take X, right, and scalar product. So maybe to do it faster, and that retains the shape of the terms that we copy here, and So all you need is to remove the first function, which is 1, and replace 1 by x, okay? And so that's what Kevin said. Okay, so this is 2 equations and 2 unknowns. So the next question is, how do you find the coefficients in the graph matrix? Of course, you can rearrange what is written here in matrix form, and that is put the coefficients C1, one scalar product with 1, and then one scalar product with x here, x scalar product with 1, x scalar product with x, okay, and have coefficient C0, C1, and then on the right hand side we have these. Okay, that's it. And so the matrix here on the left is the gram matrix. But now the gram matrix is with functions and no longer with vectors. Okay? And these are the scalar product of functions. So how do you find the scalar product of function 1 times itself? Let's say over the interval of interest here, and the interval here is from 0 to 1. Okay, let me remind you of the formula for scalar product. I think I had it somewhere before. I think it's section 7c, but let me rewrite for you here. You know, if you take the scalar product between f and g, that is simply the integral from a to b of fx gx dx. I have a set of lecture notes in which I explain explicitly how you see the integral of 2 functions as the equivalence of taking the dot product between 2 vectors. You know, that requires knowledge of numerical methods and integration. But let me leave it. If I have more time towards the end of the course, I will do that. But for now, you can accept that this is the scalar product between 2 functions. So the next question would be, how do you apply this formula and compute the scalar product between the function 1 and itself? Anyone? This is a very, very simple. While I prepare my notes, you can think about that and contribute. How do you find the first coefficient? 1 scalar product with 1. That's not number 1. That's function 1. What's the difference between function 1 and the number 1? Can anyone articulate that? What's the difference between the function 1 and number 1? There's a big difference. The right?
That with number 1, that's the base unit, such as it's just representing 1, while the function means that the output is 1.
The output is 1 for a given input.
Where there is no input in this case.
No input in this
Kind
case.
of like the range.
Range. Okay, anyone else?
Where I think of it, 1 is just like 1 like a number, and the function of 1. If you were to graph a function of 1, you just graph
Very
it.
good. It's a constant function with the value equal to 1, yes. You know, if you want to think about input, you can think of x as the input, and so whatever input, you always get the same number 1. Okay, so it's a constant function. And so, you know, what is your name and team number? Sorry.
Team 7.
Team 7, yes, Team 7, now I remember. And that should be Nick, right? Okay, very good. So therefore, how do you find the scalar product between the function 1 and itself? It's just the integral of 1 times 1 integrating over the interval from 0 to 1, right? And that's 1. Okay. So how about 1 and x? That's simply 1 times x dx, and that's x squared over 2, evaluating between 0 and 1, and that's 1/2. Okay. Can someone do x? Do the scalar product between x and itself. Quick math, and really, I just you need to remind Richard. Okay. So Richard, Mark, anyone else? Yes. What is your
Sean, team 1.
Sean, team 1? Okay. So let's start with someone who contributed. Let's team 1. Let's see. Yeah. Okay. Yeah. Sure. Go ahead.
It would just be x times x, or the integral of 0 to 1 time of x times x.
Yeah, x times x. So x times x is x squared. When you integrate up, that's x
X cubed over 3.
cubed over 3, and evaluate between 0 and 1. What's the result?
And the third.
1/3, right? So 1/3. Okay, and so therefore you have this matrix here, which has a name, and the name is associated with a famous mathematician. It's called the Hilbert matrix. And the Hilbert matrix of order 2, written as H, with 2 in the argument, you have 1, 1/2, 1/3. Okay, and in MATLAB you have a command to generate the Hilbert matrix automatically for any order. That's HILB. Okay, and so that's the Gram matrix. And on the right hand side, you do the same thing. You integrate B0 scalar product with f is the integral between 1 and x to the power 5. You get 1/6. And in the scalar product between B1 and f, that's x times x to the power 5. That's x to the power 6. Integrate between 0 and 1, you get 1/7. And so you have a system that you can solve for C0 and C1. Okay, 2 coefficients and 2 unknowns. So let me skip. Because once you know how to set up the system, the rest is simple. And here's the MATLAB code with the, it's really Octave, and Octave is the open source MATLAB. Okay, there's a Hilbert command here, HILB, and I create the inverse of the Hilbert matrix, and this is the right hand side, and I take the inverse times the right hand side, right? So you have the coefficient C0 and C1, okay, and this is the output. Okay, and let me go to the result here. So the output is here. This is the result of the solution. And so you just combine, right? So once you have C0 and C1, you just combine with the basis functions, right? X to the power 0, which is 1, and x to the power 1. And so the result is a straight line. And this blue line here is x to the power 5. Okay? And so that is the projection of the function x to the power 5 on the basis of 1 and x. Okay? Then you do the next step is to let's say, increase the basis to 1x and x squared. add one more basis, and you form the system. Now the system, the graph matrix. Now you have three unknowns, right? C0, C1, and C2. C0 is a coefficient for 1, x to the power 0. C1 is a coefficient for x, and C2 is a coefficient for x to the power 2. And so this is the graph matrix here, where you just form the scalar product between the basis functions, okay? B0, B1, and B2. And this is the result. So this is the Hilbert matrix with three basis functions, B0, B1, and B2, okay? So again, you see the structure 1, 1/2, 1/3, 1/2, 1/3, 1/4, 1/3, 1/4, and 1/5, okay? And so the right-hand side, you can find the right-hand side. And so let me show to you the result. The code is the same. And so here, you see, this is the blue curve is x to the power 5. And the result is a parabola that approximates closer to x to the power 5. Okay? And then you can keep increasing the number of basis functions, and you have more and more accurate approximation. So lecture summary is